So we have, it's a lot to us, I know, but for you it's probably not, 740 miles of transmission lines. And we have nearly, soon 3 times that of fiber optic cable that we own that is really Vermont's backbone for communications. This was an innovative leap the company made decades ago that is serving Vermont so well as we seek to connect our communities with power and communications.
So on that note, you know, what we're looking at is a transmission infrastructure that is much more flexible, that can incorporate different requirements, that can incorporate regional requirements, that is less cookie cutter and easier and faster to deploy. One of the challenges here is that the customer needs are growing faster than the customer infrastructure can handle.
So with that, I'm going to have the next panel come forward, assuming that they're all mic'd up. And we have talked about this quite a bit in previous gridCONNEXT, but the issues become more and more important, and that is how we use grid edge resources to facilitate communication between the distribution and transmission system. So with that, I'm going to let Kevin introduce his panel and take it away. Thank you.
Okay, thank you very much. So Mike. So my name is Kevin Schneider. I'm a laboratory fellow at the Pacific Northwest National Laboratory and a joint appointment at Washington State University. And I'll be moderating this panel today. We've got 3 panelists today. Betsy is the Director of Communications and Strategy at the Vermont Electric Company. Sanders, the Director of Innovation for National Grid Partners, and he leads the team's innovation laboratory. And Srijib is a senior scientist with the Oak Ridge National Laboratory with a joint appointment at University of Tennessee, Knoxville. National labs like to do joint appointments, as was mentioned earlier today. So the title of this presentation is really focusing on the grid edge and distribution systems. And this really goes back to some of the things that were said earlier today. We know that there's going to be a large amount of new electrical load coming on, whether it be new server farms and chip fabs, or even electrification of natural gas. And historically, that's always meant more transmission lines. And while we'll definitely get more new transmission lines, we know that we won't be able to build as many or as quickly as we probably want to. And that's where the grid edge really comes in. It becomes a very large technical potential out there. I mean, there's a lot of devices out there that have the potential to serve a lot of the needs of the transmission system. Now, not saying that everything in the future is going to be all distributed, but it's a good way to engage devices that are already out there and maybe even take advantage of the fact that you can site some of them a little bit easier. And so in the future, we'll have a mix of these. Now, this is not a new idea. We've seen a lot of concepts and pilot demonstrations of grid edge technologies. GridWise had the transactive technologies years ago. It was one of the early stage ones. And there have been a lot of pilot demonstrations that have proven this out. But the challenge is to take it from the pilot up to the widespread scale. That takes a lot of implementation issues. And this goes back to other issues that were mentioned today, things such as data and model quality. If you're bringing in data and models from a lot of different stakeholders, they're not all going to line up. Not everyone uses the same approach. So how do we use standards-based approaches so you can bring all the information together and then be able to make use of that? And then once you have that, how do you go through and figure out how to build the controls, the architectures, and the coordination to implement all these outcomes that we're really trying to achieve? And so that's really what this panel is starting to look at. And these 3 panelists are going to start to dive in and speak about specific examples with it. Betsy will be starting with some of the work that's being done up at VELCO and looking at some of the standards-based work they've been doing with the Pacific Northwest National Laboratory. Then Sandra will talk about their intelligent substation activities, and also something that PNNL has been somewhat involved with. And then Srijib will be talking about some of the standards-based work that they've done at Oak Ridge with part of this group, but also larger programs across the Department of Energy. So with that, I'd like these folks to go up and talk about specifics of what's going on, and then we'll open up to some Q&A. Betsy?
Thanks, Kevin. My slides should be loading up. There we go. So first, I'd love to take the opportunity to tell you a bit about VELCO. VELCO is Vermont's only transmission utility. So we are the only game in the state to deliver the bulk electric system. We are a very Vermont-y type construct. We're for-profit, but kind of like a cooperative. So all of our profits flow back to our owners, and our owners are Vermont's, this is kind of crazy, Vermont has 17 distribution utilities in it. So that's a lot of utilities for a small state. But so every dollar we earn goes back to the DUs, and then they are mandated to use that to lower rates. We take that position very seriously. When we look at our vision and our mission, it is all about creating a sustainable Vermont, and we lead with our people, we follow with our assets and our relationships. So we have, it's a lot to us, I know, but for you it's probably not, 740 miles of transmission lines. And we have nearly, soon 3 times that of fiber optic cable that we own that is really Vermont's backbone for communications. And this was an innovative leap the company made decades ago that is serving Vermont so well as we seek to connect our communities with power and communications. We also have 14,000 acres of rights-of-way that we get all the value we can from by co-locating projects, by taking care of the habitat, and our incredible community relationships as well. We, first mission, deliver reliable power to Vermonters. Take that very seriously, and we cannot do anything else if we are not doing that job first. We also are an advocate in our region for ISO New England to keep rates as affordable as possible for Vermont ratepayers. We are unique in the sense that we create every 3 years a 20-year long-range transmission plan for the state, which is incredibly helpful for our planning of our transmission grid and also keeping us connected with our owners and the activities that they are doing and how that is going to impact our grid, transmission grid, in the future. We host the Vermont System Planning Committee, which I invite you all to attend. It's a quarterly meeting. It is a kitchen table to discuss regional, national, and local energy transition needs. And it's also where we must explore non-transmission alternatives to any transmission build we need to do. So it's kind of an exciting time. Like, I'm usually talking about building interregional transmission lines in New England, and that's what we need to do right now, which we do. But today we're going to talk about the other end. We're going to talk about the grid edge. And VELCO is really grateful to be partners with both PNNL and Oak Ridge on this slate of projects. Vermont has incredibly high solar penetration for our state. And you can see on this chart the box on the grid that shows the ramp up. That was the great eclipse of April 8th. And that day, Vermont was partially in totality, and it was a sunny day. So it gave us a great real-time example of what happens to our solar generation when the sun goes down. The ramp up is what we need to plan for. That power quality, as we have more distributed energy resources and larger loads that come on when those resources are not serving the grid. So we look to partner in finding new technologies to bring to Vermont. And so we have partnered with, and actually I first want to quote Hugo from earlier. When you said your 5 words of real-time insights for proactive operation, that is what we are getting from these projects. And we're getting it at the distribution level. Our transmission operators cannot see the distribution level. We have no visibility into it. We have to use our gut. We have to, well, they have really good guts. Mine would not be good at this. But we have to use experience. We have to use predictive models as our contingency deck of cards. We don't know what's out there. We don't know if that 20 megawatts, or watts on the grid, is that an electric car getting plugged in? Is that a dishwasher turning on? Is that a battery? We don't know what's connected. And so we need to partner with our distribution utilities to help us see that, share that data in a collaborative way to gain greater visibility into what is happening on the grid because it's impacting the transmission grid now. We have backfeeding at more than half of our substations now on sunny days. That's new. The grid is operating differently right now, and we need solutions to that. And so we have partnered with, and Joe will like this, one of our rural cooperatives. Vermont Electric Cooperative has 33,000 members. They're based in northwestern and northern Vermont. They're an incredibly innovative rural cooperative, and we are so grateful to have them as a partner. And so we have on their system some monitors. And so all of this data has to feed in to a centralized system. We're talking about that standards-based platform. And so we are developing a common information model platform so that all of this data can come in from substations, from DERs, from storage, from cars, SCADA, get in the soup pot, get mixed up, and then we can use it. We can use it in an accurate way. We can know what it's all saying, how it interacts with each other. And this is going to help keep us ahead of emerging federal reliability standards. It can increase our collaboration as we prove that this common information model can deliver value to our grid operators, and it can help integrate renewable energy into grid planning as well. So this project specifically has two sensors well, it might be more than two sensors. It's sensors at two solar facilities in Vermont Electric Cooperative territory. That Vermont Electric Cooperative is sharing the data with us when they see fluctuations. And you can see the rainbow graphs are the distribution level value. So you can see the voltage, it should be below that dotted line. And pre-installation, post-installation, the voltage the power quality is so much higher. And then we can see at the transmission level value, the load power factor is so much smoother. And this is just on two, but it's proving it out. Vermont is open for innovation and experiment, and we welcome all partners, and small projects can make a big difference for us and then be applied elsewhere. So I think I'll stop there. Love any questions later. Hopefully I'll be able to answer them, but if not, I know that my national lab partners will be able to. Xander?
Great. Should I press the green button?
Yes,
Good to me?
that's what's working.
Next. Is mine up? Hello.
Second presentation.
How are folks doing today? Who flew away from the farthest? Do we have any Alaska utilities here? No? Okay.
Going back, going.
Start riffing, do crowd work. If you can't find it, I can start. Oh, here we go. Great. Hi, folks. So my name is Senator Cohan. I head up the Innovation Lab for National Grid Partners. I'm not spending too much time on National Grid because I assume you folks are familiar with who we are, but we are if I can advance this, that'd be great. One more time. We are a largest utility with operations in Massachusetts, New York, and the United Kingdom. We operate both transmission, distribution, and gas networks. We also have some unregulated components in the form of National Grid Ventures. My group, National Grid Partners, is an organization that sits basically at the nexus of new technologies and new business models and our group strategy. Our goal here is to find new technologies and new business models to help National Grid reach its aspirational goals under sustainability and the energy transition. When we start looking at the scope of what grid needs to accomplish in the coming years, the next coming decades, it becomes really apparent very quickly that if we keep doing things the same way, we're not going to get the results we want. In fact, it's going to be a very rough transition. So that results in our mission. So we've been working very hard on our innovation mission, which is to accelerate scalable solutions, cultivate trust and collaboration towards decommodation, and ensuring a clean, fair, and affordable energy future. What's really important about this is that we are focused not just on technology, but we're really focused on addressing some fundamental business challenges and market challenges that will enable technology not only to be proven out just as a pilot, but also proven out in the marketplace, right? So scale and think about commercialization. So how do we do this? Well, our team, National Grid Partners, and especially the Innovation Venture Acceleration Group, is split into four big segments. And I'll touch on the first two really quickly because they're not here, which are our investing and business development group. So we run a fairly traditional corporate venturing group that goes out and makes investments in early stage technologies that have strategic and growth value to the company. These are things like Line Vision, which is a company that we invested in to help increase dynamic line rating, increase line capacity on our transmission lines and find ways to not just have to build new transmission lines, but also better utilize and expand the capacity of the infrastructure we have. We also have a business development team. The critical piece of the business development team here is it's one thing to make an investment in the company. It's another thing to encourage their dissemination and evolution inside National Grid. So they are effectively a landing party for both our portfolio companies and more established companies who want to do business with National Grid. Their job is to really guide through the terrible gauntlet that is the utility sales cycle. Moving on to my team, which is the Innovation and Venture Acceleration team. So I head up the innovation team and the innovation lab. And the real short way of thinking about the innovation lab is that whatever we cannot find in the marketplace that is a good solution for us, whether it's through partnership or through a venture investment, we work out and build ourselves. So my team spends a lot of time working with our business units, identifying critical challenges in their technology and evolution roadmaps, and pulling together the requisite partnerships, whether it's early stage startups, whether it's national laboratories, whether it's the Department of Energy, and putting together new and novel solutions to do that. And then thinking about them in terms of products, really sort of how are we not just sort of proving out a really cool technology idea, but proving out a really cool technology idea that solves, that moves the state of affairs forward, that solves a business problem, and then allows us to see real and measurable impact for a complex system like ours. One piece about this work is we work in fairly short cycle pilots. The idea here is we really ascribe to the idea of minimum viable product, so with an emphasis on minimum. So these are fairly lightweight projects, and the goal there is that at the end of the day, we have enough empirical information to make a credible commercial decision, right? Either to scale up as a product or as a standalone company, or to make a credible argument, if in case of a regulated business, make a credible argument to our regulator and our management that this is something worth investing and worth the attention and trust of our customers. The last piece here is our venture acceleration group. There are two pieces to our venture acceleration group. One is packaging products, so taking the results of our innovation team and turning it into something that is useful not only for National Grid, but also for perhaps the market at large. One benefit of our business model, guys, is that we're not necessarily competing against each other. So solutions that we come up with could benefit others. And so part of this is finding and creating a mechanism for us not only to build new ventures, but also build new ventures that can then be used in other jurisdictions and other support where we are not necessarily the utility. The second part about that is collaboration with utilities. So the venture acceleration team actively manages partnerships with like-minded fellow travelers in helping solve some of these critical business problems. So on to the meat of the conversation. What I'm here today to talk about is our intelligent substation project. This came out of a really basic need, which is that in order for the energy transition to occur, in order for us to be able to accommodate a wave of distributed energy resources coming up from customers large and small, we need to have the infrastructure to do it. Sorry, I need to go back. Well, I can talk here. We need to have the infrastructure to do it, right? And it's getting more complex. It's not just a linear conversation where energy is communicated from a generator down through the distribution network, transmission distribution network, and to a customer, but we actually have a more interactive and transactive network. I'm going to go rogue then. We have a more interactive and transactive network.
Is there a way to go back a couple slides?
Yeah.
Oh, there we go. There we go. Look at that technology in play.
Just hit the back.
So on that note, what we're looking at is a transmission infrastructure that is much more flexible, that can incorporate different requirements, that can incorporate regional requirements, that is less cookie cutter and easier and faster to deploy. one of the challenges here is that the customer needs are growing faster than the customer infrastructure can handle. I know what's happening right now is that there's an animation in my slide deck that I forgot to take out. So what does this start to look like? What this starts to look like is a movement away from a hardware-focused and hardware-forward substation design, and one that really looks at a software-focused design that focuses on principles of edge computing and virtualization to design systems that are fewer racks, less on-site maintenance, and more virtual maintenance. So ones that can do a lot more management of complex systems along the grid. The reason you do that is mostly from data needs, right? So you're not communicating huge amounts of data back to centralized locations. And the central one is speed, right? So you're handling a greater risk profile along the edge of the grid and making these decisions, assisted by automated systems to allow you to handle the fluctuations and the heterogeneous nature of distribution grids along the edge. Where we are with this project right now is that we are working on the virtualization and edge computing components alongside Pacific Northwest National Laboratory and other partners. But what my team has been tasked with is sort of think about the larger commercialization and grid expansion aspects of it. So the idea of a localized, virtualized substation and calculations along the edge of the grid is, I think, the really important piece of this project. But there are other things around it that are also really important in terms of communication networks, in terms of cybersecurity, in terms of workforce training, and how we're going to build this thing. So it's one thing to build one of these, it's another thing to build several hundred or several thousand of these along the grid. But we think it has real importance here because I think it's something we're looking at as an extension of our digital substation activities. So i.e. 61850 is the first piece here, but really looking beyond that to extending it, extending that philosophy towards a much more and broader software-driven grid. So it's a little bit far out, but I think in the long run it will bear really important benefits to us and to the customer by creating an environment that will allow us to incorporate and expand as the needs of our customers expand. I'm happy to discuss all sorts of benefits in the future, but we are looking for support and partnerships along those lines.
Sandra, I've just been told we've actually got some extra time.
Oh,
so if you want to talk
fantastic.
a little bit more, but I've got a question of how do you coordinate the changes that occur on the substation level with back at the central control to make sure they don't get out of sync with one another? Just to tee up, maybe talk a little longer.
Yeah, sure. I can talk a little bit longer about that. That involves computing all along the value chain there. So I think part of it is that instead of having a centralized control room, you're instilling logic at each point. So you're incorporating data sources and data feedbacks from the customer site and the DER site specifically, but you have really involved, intense software logic at the substation edge that is supporting the operator decision, right? So it's supporting and making some advanced decisions and operating tighter tolerances where you're making milliseconds long decisions. But then what happens is that logic is incorporated all along the grid rather than the central place. Should I pass on this?
I think so.
Yes.
All right. Hi, good afternoon. I have no presentation. That's all right.
And feel free to take more than the 10 minutes we decided.
That's right. All right, let's see. We got that. I think it's coming on after this. Give it a second here. Well, my first slide is just my name and where I'm from and all of that. So I'll just start. Yeah, my name is Srijib Mukherjee. I'm a scientist with Oak Ridge National Lab. We are one of DOE's 17 federal labs. Pacific Northwest National Lab is a sister lab. We haven't done anything special besides build an atomic bomb and 4 elements of the periodic table, and a whole bunch of Nobel laureates. So we got some real brain power questions. So anyway, so grid edge resources to facilitate coordination between T&D. So this is a project, just like my colleague, she was speaking about with Vermont Electric, with VELCO, and with VEC, and in coordination with PNNL. We were doing some associated research with that, and some challenges is what I wanted to share. So that said, this is an Office of Electricity funded project through DOE, and it involves two parts, and one of them my colleague already talked about, and it involved the Maple Leaf, which is part of the VEC's, VELCO's project, in leveraging smart meter data at the field level to study the efficacy of what we call under-frequency load shedding. So under-frequency load shedding is a principle in the older days. If there was an under-frequency problem, the load would shed. However, that concept is very changing on a daily basis because of the integration of distributed resources. DERs, distributed generation, virtual power plants, microgrids, things like that. So what's happening is it gives you a spurious signal. So UFLS relays don't actually trip appropriately when, let's say, a DER is probably feeding downstream assets and hasn't disconnected. So there were some design practices associated with that we were trying to streamline and make into a better controller. And then the second aspect of it was Maple Branch, which evaluates an innovative way to improve ISO New England's OP17 procedure standard. And this again comes back to standards-based practice, what my colleague was talking about, in evaluating or improving load power factor. So we compared solutions to traditional infrastructure upgrades to solutions using grid-friendly inverter behavior, because we're going to synthetic, you got rotational inertia, and you got synthetic inertia with inverter-based resources that are coming from wind and solar generation. And then trying to control power factor, not by traditional methods such as kick capacitor banks, but use other technologies such as what we in rotational machines typically use a PQ curve, D curve, but IBRs can use something called a volt-var curve to improve system flexibility. So these are some demonstrations with that. And so the idea of common information modeling is really what's happened is we've had these traditional boundaries. We all know that, right? I've been around the grid for 35 years, so I'm pretty familiar with it. So you get generation, you get transmission, you got distribution, so the vertical integrated concept is disappearing. We're moving to a distributed architecture. And the world is changing in many, many, many different ways. You can see transmission, centralized mesh network, balanced power flow, complete model, blah, blah, all of that. So, and then you got distribution, you got radial feeders, you got an unbalanced power flow, you got geospatial asset mapping, and then you got frequent changes associated with that. So if I take that, these silos are power system functional entities. You can see have different entities tied back with it, right? So from generation to transmission to distribution, you've got regulation entities that are required by regulatory authorities to maintain, be the provider of last resort. You've got reliability coordination with the ISOs and the RTOs. You've got energy services. You've got markets, which are happening both at the wholesale level, and now it's coming to retail. And then you've got control and coordination. So you can see over here in this particular diagram how these things are changing on specifically in the distribution side. You've got distributed generation, you've got we're thinking about actually energizing systems from the bottom up. What's the traditional way of providing power? Generation to transmission to distribution to load. How about powering the system up from distribution to transmission to the grid? So black starting the grid from distribution, having DSOs, distribution system operators, control from the back end side of actually controlling the grid. So you got aggregators coming in. We talked about the issue and challenges with data centers. The other significant challenge we didn't talk about, which I want to just touch base quickly on, is the advent, which is already conducive and incentivized in a market like ERCOT, is Bitcoin mining. Bitcoin mining has become very prevalent. The people going out with high computational needs, which are energy intensive. It calculates a hash rate and actually tells you for being a load management resource. So it's demand flexibility. Think about it this way, right? Imagine if you had, in my case, it's Duke Energy, they put a controller on my HVAC system, but that controller says that, hey, you are allowing me to put your load off during peak demand times. I'm telling you that you take my load off, you pay me money. So Bitcoin miners are there to make money. They're not there to keep your lights on. So that concept's got to change, right? I'll take your load off to improve your demand, meet your needs, and then that's how I'll make money. And then power system software. So you can see over here, the old traditional ways of generation was what? AGC packages, unit commitment, economic dispatch, those kinds of activities tied back with energy change scheduling packages and reserve monitoring for spinning and operating reserves. And then you have EMS displays that go back into transmission and SCADA. SCADA and real-time network analysis, that ties back with that. And then you have the DMS side, which is crew dispatch, fault location isolation, FLISR, VOLVAR, and then you have outage management and EMI metering that actually goes back to the distribution side of things. I got a minute and a half, so I'll just quickly go to the next slide. I just want to bore you.
You have more time.
I have more time? All right. Okay, so basically, these little software packages have been the traditional packages. But what you're seeing is disparate data. So what we're trying to do with our partner utility and create that as a package that eventually can be used in the grid is create a platform for uniformity, for bringing uniformity to all these models and disparate data that you have, because the challenges are great and the distribution of generation and transmission is completely changing. So with that in mind, if you look at this, this is actually a reference, not Oak Ridge, but I don't really had the old presentation, but a reference to Pacific Northwest National Lab. This is where the picture comes from, so credit to them. It's not Oak Ridge's picture. Is EMS, ADMS, network planning, GIS, customer billing, asset management, spreadsheets. You can see each sets of data are disparate. And what you're trying to do is trying to work through this package called a gridCONNEXT to actually bring them all this information into a common platform. And that's what it is, so that it can be used by any developer, software developer, any model who wants to come in, anybody comes in trying to make that. So it becomes a uniform parity for everybody to come and use it. So it's open access, basically. So silos, we got utility system operators, you got operations engineers, application developers, and then you have cyber, of course. So what you're trying to do is trying to build all of them in doing this. This picture also credited back to PNNL. For some reason, my newer presentation didn't get in. And then that's what the past looks like. This is what the future will look like. Won't do that. So we're trying to do generation, that's the past. You can see over here, everything is connected with the internet. And you have the grid. So the past looks that, now the future will look something like this, which is more of a distributed architecture, a form of a distributed architecture, an emerging rich data environment. So consensus-based vocabulary, quickly wanted to go through that. So it's a consistent identifier, property and attributes, then associating measurements of devices correctly, and then correlating those devices to where they're coming from, and then having a context for that data, and then sharing it in a format that's understandable and compatible in all forms. Yep, these are some key organizations, and that's about it.
Okay, thank you very much. Yeah. So before we open for some questions, I did have some questions for the group based on what you talked about. There was a lot of discussion around what some of the technical challenges are, and there's clearly some work going on. But when you look at the near-term potential for problems that the grid edge can solve, I know VELCO's looking at some specific ones with OP17, with New England ISO, and power factor correction at the T&D interface, but also looking at the under-frequency load shedding, and the intelligent substations looking at how you can do some reconfiguration and things of that sort. But I'm wondering, can you talk more about what you think some of the other near-term opportunities are for the grid edge to be solving or displacing existing transmission solutions that maybe we can't get in place in time? Anybody want to take a swing at some of those?
Oh, this is still we know that regulations come after incidents, right? So our goal is to keep the power steady so that we don't have inverters. When we saw this, so we saw an inverter trip in upstate New York that we saw, and then our grid flipped all out of nowhere, and you could see the spread of this one inverter tripping in New York spread throughout all of New England. So we need to be able to see that now and know what's happening now, because if we don't, NERC will come in and tell us how to do it. So we want to make sure that we are staying ahead. And so it's really power quality, it's dynamic line ratings, it's ambient air ratings as well, and it is keep making sure that the grid we have now is operating solidly as it changes, and it's changing. And so we are trying to stay ahead. We don't have a lot of load growth in Vermont. We all have these great state policy goals, and we are trying, but it's not happening as fast as we thought it was going to. So the growth hasn't quite shown up and is not causing too much drama yet. But that is something also we want to stay ahead of as we really hope that kicks off.
So with respect to your comment of looking at the visibility in your system, I doubt VELCO has a plan to put sensors all over the system immediately.
I mean,
Well, possibly some, but I guess a question would be, is there a willingness to make use of sensors that VELCO doesn't own, non-utility owned assets, and make decisions based on the information they see coming from those?
the answer to that is yes. There's a lot of talk in Vermont right now around data governance, data sharing, the trust in where the data is going. We're talking about that with some of our own owners. What are you going to do with our data? Are you going to sell it? No. So we have work to do to build a data governance model for all of this incredible data that's out there and that we need to share and collaborate on.
And I guess pulling on that thread, Sandra, when you look at the intelligent substation approach, I assume that could potentially involve non-utility assets as well. Sure. Do you have some thoughts on the data governance and where you might go with that?
I have many thoughts on data governance. I think data is really at the centerpiece of all of this. And when you talk about near-term aspects, I think one thing that we're working on in the near term, as we are sort of working out the infrastructure for intelligent substations, is really getting better visibility into what the grid edge looks like and how that impacts planning and design of our system, and then ultimately of tariff and regulation, right? So really sort of being able to build out the capacity, first of all, to pull in those external data sets and understand how tangential data sets can interface with things coming out of our actual system, incomplete data that's coming out of our system, and to provide us with a comprehensive and perhaps a different view of how our operations work along the edge of the grid. Data governance is a big piece of that at the end of the day. I think part of it is making sure that we focus on data fidelity and on up-to-date data, and how do we incorporate and ingest those and share them across various platforms and planning tools that we use.
And Srijib, I know that you're working with the Office of Electricity on a number of activities at how do you manage the data across the T&D boundary. Can you talk to some of the challenges you've seen there and some of the opportunities and the solutions that have been presenting themselves?
Great question, Kevin. Thank you, Dr. Schneider. All right, so I'll talk from an engineering perspective, okay? See, one of the biggest challenges on the T&D interface that you have is the transition from rotational inertia to synthetic inertia. So synthetic, how many of you are engineers? Probably, I don't know how many people in this room are engineers, but The engineers don't understand. The problem with inverter-based resources is fault contribution, short-circuit contribution to faults. So that correlates back to something called grid strength. So lack of grid strength that a rotational magnetic field creates cannot be created by synthetic power control, electronic controlled inverter-based resources. That has a significant challenge to how that interface is operated, or how the curves are run, or how fault contribution is addressed, or how protection control settings are done. Those are some of the significant challenges I see that lie ahead. And one of them is already being addressed by Pacific Northwest National Labs with us, is the under-frequency load shed issue and predictive load shed, predicting a load curve. The load curve that we'd have in the summer or in the spring, summer, shoulder months, winter, is no longer valid with DER resources on feeder circuits. So how are you going to predict that? Again, that boils down to data governance and how that's going to be implemented. But power quality, along with grid strength, are the two key issues that I see, and harmonics, of course. But those are the key issues that I see within the T&D interface.
And do you see data needs for exchanging that across the T&D boundary?
Yes, I do. Absolutely. So the data needs are going to be pretty, like you said. And sensors solve some of that problem, but some of the problem data sharing can be induced by a better platform of having a common information model for what I call interoperability. So interoperability, which is what we're working on, interoperability of devices talking to each other, context of what they are. PMUs, phasor measurement units, who are they talking with? Or if you have another, we throw these buzzwords all over the place, without meaning or relevance. Who are they talking to? What are they doing? What data are they gathering? And how are they interoperating? Getting to a common platform and aggregating that data is going to be key to making this successful.
And I know ideally you have these models that have all the information you need and the system operator can make choices. But Betsy, a question I'd like to bring up, looking at Green Mountain Power, I know that they have a contract with Tesla where they have, I believe, purchased Tesla Powerwalls, put them in the customers' houses, but then they can operate them for their own operation. Now, when I say they operate them, they can call up Tesla and ask for Tesla to operate. And so they're getting a certain performance envelope out of it, but they don't necessarily have what we'd consider the traditional information that a utility planner or operator would want. They don't have a SIM model of what the device characteristics are and all the controls. They just get an assurance of a certain level of operation. So the question I would have, and this will be to you next, Sanders, within the utility environment going forward, how open are people to the idea of having critical resources that you need be under the control of another entity that is telling you, don't worry, we'll be there, and you have to work through an agreement that will be the case?
I'm glad you brought it back to people. We can do all of the modeling, all of the engineering, all of the science we want. We need people to change to be able to do all of this. And culture has to change. The culture of change management in utilities has to get stronger so we can do some of these things. And
so real quick to clarify, when you say people have to change, do you mean the customers or the operators?
yes.
Okay.
Yes. The people I sit with every day, the ones behind the locked doors, the operators, the engineers, yes, we all have to change. We are all, smart people. We want to do the right thing and we want to do the best thing, but we have to change to be able to do that. And I think oftentimes, I actually launched that program at Green Mountain Power. I was there when we did that Tesla program, starting putting those batteries in people's homes. Early adopters are there for you, but then we get up the hockey stick and we can't get farther because it's why? Why me? Why now? Why do I need to do this? So I think there is a huge cultural component that we often miss when we're designing and implementing these programs. And you're right. The first time my house isn't warm enough, I'm not doing that anymore. So you have to give people choices and give them the feeling of control and power to get the benefit for the grid as well. It has to be a partnership.
Sandra, any thoughts around the substations?
Yeah, a lot of thoughts around the substations. I think a lot of change, and I have to echo your sentiment there. I think that there's, one critical thinking around the intelligent substations is that it creates a common data platform. When you push things towards a software-based solution, it allows you to create common standards all the way up the value chain, right? So, one question I would get from folks, when we were discussing this project is, well, what voltages, of substation does the intelligent substation apply to? And it's kind of them all, right? It's the idea here is that you can apply these generalized concepts all up and down the value chain. And so what that effectively allows you to do in broad sense is blur that boundary between transmission and distribution, that you can apply similar principles to a transmission substation that you would to a distribution substation. In theory, right? Life is a lot different. I think, one thing that we have to work on is again, changing culture, changing business culture, absolutely. Creating mechanisms and creating really appropriate data governance standards so you're not using 15 different systems depending on where you are, what legacy equipment you're working with. Really sort of being able to provide common platforms that will allow you to supplement data sets where they fall short or add data sets where you need more additional information. And that provides a lot more of that balancing communication that you would need along the edge of the grid. I think part of this also is a regulatory piece. I think one challenge that we're finding, not necessarily within the boundaries of the intelligent substation, but sort of within the boundaries of overall electrification and thinking about holistic ways to expand and manage a grid that is governed by heterogeneous DERs that are all doing various different things and have various different impacts on the grid, whether it's a data center or your home electric vehicle charger or your stove, is data sharing across institutions, right? So really finding ways where you're looking to provide reliability and benefit to the customer, but in National Grid, for example, we have gas customers, we have electric customers. They're not necessarily the same people, but the data sets could actually benefit each other.
Yes.
There are specific regulatory blockages in terms of our affiliation rules that makes this sometimes a little bit difficult, where we have to engage with our regulators and our earlier than we would like to. Put it that way.
And Srijib, last question on that is, when you talk about back to the models again, we have models out there like the Common Information Model that are very good at known structures. But as we start to move into these new concept of, it's not just a battery, it's a portfolio of resources with some certain uncertainty envelope, maybe. What have you seen in work being done along those lines that might be able to support these ideas and their actual implementation?
Sure. Well, a couple of technologies. First example is batteries, right? We talk about batteries. Batteries is one form of storage. Who knows which is the greatest form of storage, energy storage that's out there right now? Which is the greatest form? It's not battery. Who can tell me?
Water.
Pump storage, water, exactly. Everyone will think battery, this, that, all of this. It's pump storage, it's hydro. All right, that's one concept. Second concept that I wanted to go through was energy. When you talk about energy, it's not just electrical power. That's just a blip. It's electric, water, gas, telecommunications, cyber, that's energy. So you have to look at it holistically. It's interdependent to each other. It's connected. So data sharing amongst all of those is crucial. Going back to Kevin's question about batteries, you're seeing technologies coming to vehicle-to-grid electrification. So you got a Tesla 85 kilowatt hour battery pack lying in a garage. You can blockchain it with a neighbor, and that is sitting inertia in your garage. That sitting inertia that can power your house during a black start, during a hurricane, making extreme weather resilient. That's how you create a system that's actually more for distributed architecture, actually doing that. So vehicle-to-grid charging, vehicle-to-grid electrification is a huge part of what the new grid's going to look like, and being energized and moving forward, actually being controlled by distribution system operators. That'll tie back to resizing service transformers. Like a resiliency tied back with service transformers that are a big issue. So those are the challenges that we're seeing coming ahead.
Thank you very much.
Yep.
With that, I'd like to open up to questions to the audience. Are we back on schedule or? Okay. So we'll take questions until it's time for the next group then.
Yeah, we got one there, I think.
Hi, I'm Dr. Shankar from SAF Batteries in Paris. I think complementing to what Srijib mentioned, he did say about inertia and system strength. Again, of course, system strength is a steady state phenomena. I wouldn't go there, but the second part of it, which is again, it's going to be a paradoxical situation when you go with grid forming inverters, is you're going to deal with system strength, of course, has to provide the voltage stability for the controllers as well as the voltage availability. So that's on one hand, low voltage right through. Mm-hmm. But then there is also cancelling of negative sequence components for the protection. That's going to be the challenge because in Europe, in Australia, everywhere else we are encountering these problems. And perhaps I think it's a wee bit late in the US. These things are picking up, but we are dealing with real situations there because if you're going to actually provide the component, then you're going to compromise on the low voltage support. Because again, without going into the intricacies of the controllers, you're only going to deal with the direct and quadrature component there anyway. Right. But the real problem between transmission and distribution, I think, which is glooming, is for the likes of ERCOT, transposing that ERCOT and CAISOs and etc. is when you have grid forming inverters, this is going to be a real problem. Protection engineers are going to say that,
yes.
Oh, the protection hasn't operated. It's happened in New South Wales corridor.
Yes.
One of the protections never operated because, of course, we can actually switch over to transient-based protection. So this is something that we need to deal with. And maybe the likes of PNNL and yours and the other NREL should start also, because I tried to see that. Are these guys addressing? And now coming to the PCS manufacturers who are dealing with, so 3 Ps which needs to be, one is power system, the other is power electronics, and then third is protection. I think you'll get 2 out of 3 logic here in terms of the skill sets. That's something which also needs to be upscaled or something. And therefore, we are dealing with the situation in UK. We're dealing with this situation in Australia, in New South Wales, or the other 5 utilities. So this will not be too far, because if you then look at Teslas, they don't actually measure using PMUs for rock-off. Yeah. They actually derive these components. Yep. So these are some things that, subtle differences that perhaps I think, because I tend to see that US is catching up on HVDC as well as on the grid forming. Yeah. Perhaps there is a lot of things from the use cases, real life use cases from Europe to be transposed here. Yeah. That would be my perspective.
I 100% agree. 100% agree with you. Everything you said is accurate. And thank you.
And I think with that, we are out of time.
One more question.
Thank you very much, everyone.
Yeah, one more question here, actually. One more
we do have one more, okay.
Tonight.
Hi, Michael Downey. Whoa, hello. Michael Downey with the Energy Futures Initiative. We're a clean energy think tank here in town. A lot of the technologies you all are talking about are great and will enable a lot of improved grid management, customer benefits, et cetera. But a common refrain that I hear is that when we look at utility incentives and regulatory models, that making a lot of these investments often aren't aligned with what your financial incentives are. So I don't want to ask about whether your company's incentives are aligned, but rather when you zoom out to the industry, are you seeing any emerging models that are coming out of either better regulatory engagement or better utility engagement, such that the incentive to do a lot of this grid edge work really is the most beneficial and profitable option for the utility itself?
I'll go ahead and take the first cut at that because I'm not at a utility. I think it's obviously in the U.S. it's going to vary location by location, but I think where you're starting to see that occur, the increased alignment, is where the traditional approaches for solving these problems is no longer working. As it becomes harder and harder to build transmission and there are no other options, the regulatory body starts saying, what are the other options? And they start evaluating those. From what I've seen, people that don't have those pressures, there's not a real, something has to drive them towards that. Otherwise, they're not just going to do it because it's a really neat technical approach.
I can talk about us because that's what I know best. And you're right. And so we are incentivized to invest in capital, which is where these projects start. And then these projects very quickly flip to expense, where we do not earn a regulated rate of return on it, and it is all borne by our 17 distribution utilities. And so we are in parallel trying to explore new financial models and trying to figure out new ways to finance this that we can still give the benefit to Vermont, but not take all the value away by just using a line of capital, which VELCO could very well use. But that doesn't benefit our owners either. So it is a parallel conundrum that we are seeking to solve too.
I got nothing.
I think broadly speaking, I think we're in a similar boat. I think that there's, not speaking specifically about National Grid, but in general, I think that there are, one thing that I think the discussion of this panel has sort of described and touched on, as you point out, is that our customers are different. And our customers have different needs and different incentives. And so even when you're stemming from this mission of building out a reliable and affordable grid for everybody, we can't get there under the current incentive structure, right? There's just not enough, literally not enough time, people, or steel to do it. So you have to start thinking about different ways. And so you have to start thinking about regulatory models that, and this is somewhat my opinion, regulatory models that get at the heart of what people need from the grid and what specific customers need from the grid, whether it is increased reliability, whether it is increased resiliency. So the needs of a data center with 5 nines reliability is probably very different from the needs of your average residential customer. And so how do you shape the incentive on the grid so that it relies more on really what we're trying to get at in terms of customer benefit and safety and security, rather than sort of straightforward capital recoup.
Yeah, I pretty much echo everything that the other three, including what Kevin had just said, which is just about accurate. But nothing else of value to add. So they said it.
Thank you very much.